basically, BHeap is a classic binary tree with the essence of memory tree addressing, where the value of m depends on the memory page size. The value of m is equal to memory page size divided by 2, because each of the memory page have m different child pages. Now heading towards the definition says a BHeap is a binary heap implemented to keep a subtrees in a single page. The definition wants to say that we want to accommodate more and more child pages into a single memory page, because more the pages, more the page fault takes place, and we here want to actually reduce the page fault. So we are reducing the pages, and thus the basic idea of the BHeap is to reduce the visited number of memory pages. Here we got to know about the binary heap and the BHeap. Now we will study how the binary heap and BHeap are used in a virtual memory. Before that, we will study what is virtual memory and what is traditional memory. Virtual memory is a memory management technique that creates an illusion to the users of a very large main memory. As you can see in the image right here, there are various memory pages, and these memory pages are mapped to the memory map, and finally they are mapped to the physical memory, and physical memory then it is mapped to the physical memory chunks. This is how the virtual memory works. Previously, the traditional memory mapping were done in the contiguous manner, how the arrays are allocated in the memory in every different levels in the every different pages. After having an idea of virtual memory, we will now further discuss about the modern memory storage into the computers. As we all know, the modern memory uses heaps and trees for allocation of the physical memory chunks. So, according to that, memory is organized on the modern computers into pages in virtual memory. This scheme of laying out the binary tree can be highly inefficient, because a common operation on a binary tree is a vertical traversal. Due to the vertical traversal in the binary heap, problem rise in the usage of binary heap in virtual memory. Let's discuss that problem. As we know, in the binary heap, we traverse vertically through the levels till we get the search node. But this traversal in the modern era of virtual pages is highly inefficient. There are two reasons why we should not use binary heap in the virtual memory. The first is that because the distance while we going to depth becomes exponential. As you can see in the animation below, this is how the binary heap grows. It grows exponentially. Like in the level 0, there is only one node. In level 2, there are level 1, there are two nodes, and level 2, there are four nodes, and level 4, there will be 8 nodes, and thus it grows in the power of 2, which becomes exponential. The second reason is that every node will be on the separate memory pages. This increases the memory page faults, which are very expensive. Now we were discussing about why should we not use binary heap for virtual memory, but after this we will discuss why should we use BHeap in virtual memory. We use BHeap because BHeap solves a problem of binary heap by laying out the child nodes in memory in a different way. It tries to position the subtrees within a single memory page. Therefore, at a single vertical traversal, several of the consecutive nodes will be retrieved on the same page, which leads to lower number of page faults. As you can see in the image below, yes, as you can see over here, the as the eighth node is not splitted into two, therefore there is not an increasing level. So as there are less number of levels, there will be less number of pages, and thus the system can easily search the particular node which it wants. Now we will see how the BHeap was introduced. Paul Henning introduced the BHeap when he made changes in the binary heap which were parallel to the binary tree to B tree conversions, and that invented a variant called BHeap. The difference between the binary heap and the BHeap. In the context of performance, the creating and expiring objects are relatively infrequent actions. Once created, objects are often cached for weeks, even not months. Therefore, binary heap may not be updated even once per minute, or also some not even once per hour. As the gigabytes of data or objects are delivered to the clients, and these objects will all compete for the primary resource. In worst case, the binary heap average 11.5 page transfers per operation, while BHeap needs only 1.14 page transfers in SSD. If we are using mechanical hard disk, the rotating platters would change the ratio, and ratio varies up to 110 and 11.4 milliseconds.
As you can see in the graph, the red line is the binary heap and the green line is the B heap. So as we increase the VM pressure, the runtime decreases. But there is a significant difference between the binary heap and the B heap. Now let's study about the implementation of B heap. Paul Henningham gave two options for layout of the nodes, one in which the two positions per page were wasted but the strict binary structure was preserved, and the another was the whole available space of the pages were used but the tree failed to expand for one level upon entering a new page. That is, the nodes on that level have only one child. In any case, an important point is that upon leaving a page, both child nodes are always in a common other page. Since it is a since in a vertical traversal, the algorithm will typically compare both children with the parent to know how to proceed. For this reason, each page can be said to contain two parallel subtrees interspersed with each other. The pages themselves can be seen as a M-array tree, and since half of the elements in each page will be leaves within that page, and the trees of the page has a splitting factor of page size divided by 2. Now let's understand the parent function. The parent function have two modes. Like for the nodes of 0 and 1, they are only used in the variant which is exploiting all the possible space. In this case, the parent index of both nodes is the same. It is in a different page and its specific offset within that page only depends on the current page number. Specifically, to compute the parent's page number, simply divide the current node's page number by page tree splitting factor, which we decided that page size divided by 2. To get the right offset within the page, consider that it must be one of the leaf nodes within the parent page. So the start at offset will be page size by 2. Then add the difference between the current page number and the parent's page number minus 1. Since the page after the parent page has its parent node in index page size by 2. For nodes 2 and 3, the parent is different depending on the mode. In the space saving mode, the parents are simply 0 and 1 respectively. So one needs to subtract by 2. On the other hand, in the strict binary tree mode, these nodes are roots of the page instead of 0 and 1, and so their common parent is computed in the same way as described above.
Finally, I want to summarize my presentation. The only difference between the binary heap and the B heap is the formula for finding the parent from the child, or say vice versa. In the binary heap, the traditional way of finding the parent from child is n, where the where n is the parent and 2n and 2n plus 1 are are its children according to the formula. And vertical traversal to hit and all the vertical traversal to hit a different VM page for each step up and step down in the tree with 8 items per page. Whereas the B heap builds the tree by filling up the pages vertically to match the direction we traverse the heap. This rearrangement increases the average number of comparison or say swap operations required to keep the tree invariant true, but ensures that most of those operations happen inside the VM page and thus reduces the VM footprint and the VM page faults. There are two main points to be noted. The once we leave a VM page through the bottom, it is important for the performance that both child nodes live in the same VM page because we want to compare it both of their parents. Because of this, the tree fails to expand for one generation every time it enters a new VM page in order to use the first two elements in the page productively. These are the references I've used. The one is the Wikipedia, and the another is ACM, and etc. Thank you.